Right, well, we'll make a start then. So, last time we were talking about cubic splines and how we can use piecewise cubic curve modelling in order to fit curves to shapes in images. Last lecture we spent a lot of time looking at the mathematics around this. I just want to finish off on one mathematical concept before we start looking at the more applied side, how we apply this maths in computer vision. So you'll remember last time we introduced this framework for a cubic curve, parametric cubic curve. P of S is equal to GMQ of S, where this matrix here is the Q contains the parameter. And if we choose M appropriately to pick a family of curves and therefore assign a meaning to the entries in G, which lets us define the shape of the curve, we can iterate from S is 0 all the way through to S is 1 to draw out the path of this curve in space. And we also discussed how we can do things like calculate the derivative of this curve as well. So the first derivative of this equation with respect to S corresponds to the velocity, if you like, of this particle as it moves along the curve, the tangent to the curve, and we just get that by differentiating the equation, which of course changes only this Q matrix in here, so 3s squared 2s 1 0. And if we wanted to go on and differentiate this further, get the second derivative, we could do that. So we get like 6s, 2, and 0, 0, and so on. So we'd like to reason a little bit about what these quantities actually mean. If I were to take a wire, like normally when I do this I have a long wire to hand, but we've gone a bit too digital now, so we don't have that. I can use a phone wire. Okay, so imagine that this is my curve from P is 0 all the way down here to P is 1 at the end. This is some parametric curve, so it's a root in three-dimensional space. So the entries in my G matrix will be three-dimensional vectors, and it'll output a three-dimensional vector in x, y, z as well. Then at any point I can iterate on this curve by increasing my s, and that'll take me along my curve. At any point, I can apply this equation P dash of S, which is my first derivative, to calculate the tangent to my curve as I move along it. And then if I think about it, if I have this curve going through space, I'm looking at the tangent to this curve. If I have a curve that bends quite a lot, has what we call high curvature, then as I sample my tangent to this curve, that tangent will change quite a lot as I move along the curve. Yeah, the rate of change of the tangent will be quite large. If the curve is quite flat, and my tangent will change very little as I move along the curve. So the rate of change of the tangent, in other words, the second derivative of the curve we just discussed, is somehow linked to this quantity, the curvature, and specifically it's the magnitude of that second derivative that tells us how much that tangent changes over time. In other words, what the curvature is. So clearly, reasoning about the first and second derivatives of these curves gives us useful information around the tangent or velocity of a particle as it moves along the curve, as well as the curvature of that curve. And these quantities can be united within something called a Frenet frame, which can be thought of as a natural reference frame for points along the curve. So imagine that this is here a curve, this is my phone wire that I was just trying to demonstrate with. This is a curve in three-dimensional space. Okay, as I move along this curve, I can calculate the tangent, which points along the direction of motion along the curve. I calculate that using the first derivative. But I can also calculate two other vectors, the normal and binormal, which can be considered together with a tangent to define a three-dimensional reference frame about any point P of S on that curve. So if I were, in practical terms, if I was thinking about modelling a roller coaster and I wanted to define a camera viewpoint that was pointing in the direction of travel, what I might do is align the optical axis of the camera down the tangent of the curve, and then I might use the normal and the binormal to be the x and y axes of my camera sensor, which would then define a reference frame that moves smoothly as I travel along the curve. So this frame then is called the Frenet frame. It's a useful thing to be able to compute. We get the tangent from the first derivative, the normal from the second derivative, and the binormal is actually a cross product between the tangent and the normal. So it's a vector that's orthogonal to the two of them. And those three vectors then define this Frenet frame. I have a quick demo I can show you of the Frenet frame in action. So in this demo, we have it's not actually a cubic curve, but it's a parametric curve. So instead of defining my P of S to be some polynomial, what I'm doing instead is I'm saying I'm going to have my P of theta being some trigonometric function where I'm going to get the x component from cos theta, the y component sine theta, and the z component will be theta. So this will actually trace out a spiral in three-dimensional space. Can you see that? So the x and y correspond to rotation about the origin, and then theta increases the kind of the height of the point as it's in three-dimensional space. So let me switch over to the laptop and do a quick demo on this. Okay. Where is it? In the and again, this example is in the lab code. It's frene.m.matlab. So here's my code. So what I'm doing here is I'm defining this parametric curve in the way I've just described on the board here. The sine and cosine, and S is what I was using as theta on the board there. Actually, I've got the sine and cosine the other way around here, but it doesn't matter. It's just tracing out a circle of increasing height S as it goes through three-dimensional space. And then I'm computing here the first derivative of that equation there, okay, which you can see the sine has changed to, so the negative sine has changed to negative cosine, and the cosine has changed to negative sine, so it's the first derivative of that equation. And then I've got the second derivative here as well, which is the first derivative differentiated again. So the Frene frame then, local to a point P of S, is going to have its tangent taken from the first derivative, its normal taken from the second derivative, and its binormal is the cross product of those two vectors. You all see that? Yeah? So let's run that code and see what happens. Okay, so we plotted out our spiral there. We've iterated on our P of theta from 0 to some large number. You can see the little red star is the P of S, the point we are on the curve as we increase our theta. You can see the green vector is the tangent. Okay, the first derivative of that equation, it's as predicted, points in the direction of travel. It's the instantaneous velocity of that at that point on the curve. And then the normal and the binormal are in blue and purple respectively. So you can imagine that then defining that reference frame of that camera on the front of the roller coaster as I described it earlier. Yeah, does that make sense? Okay, so what's the takeaway message? That this quantity, the Frene frame, is a way of defining a reference frame local to a point on a parametric curve. It is defined by its tangent, normal, and binormal, and as we'll see, reasoning about the first and second derivatives lets us reason about the velocity and the curvature, which is useful in practical applications we're going to come to in a moment. So then, just finishing off then that deck of slides from last time. In this slide deck, we talked about explicit parametric and implicit form of the line. We looked at different ways of defining curve continuity for parametric cubic curves. We looked at a few curve families, and finally, I talked about these components of the Frene frame. Okay, well, let's move on to today's slide deck, and this is the deck that you've got in front of you, around this topic of active contours. So this is where we apply the maths we've just covered to do some computer vision. Okay, and if you recall from my introduction last time, what we're looking at this week is this problem of fitting a curve to an object in an image, localizing the position of an object in an image using a curve. So the learning outcomes for this slide deck then are, first of all, to introduce this concept of an active contour, more colloquially known as a snake, and we'll talk about something called the snake energy term, which is basically an equation that's used to position the snake, the curve, on an image in order to snap it onto the location of the object in the image. We'll talk a little bit about how we do optimize in order to do that, using something called gradient descent, and then we'll look at a couple of other features of snakes, so for example, using the Williams-Shah algorithm as an alternative to that to do the snake optimization, and then we'll talk a little bit about statistical shape models as well. So this example here, again, I'll see if I can pull this up on the other machine to play the video, because I don't think it'll play with the lecture capture enabled. switch. So this, this image here is a medical image, courtesy of one of the PhD students in CVSSP. And the objective here is to take this image from a scan and try and establish the location of the heart in the image. Okay, and that's been done here using this red curve. And what you'll see when I play the animation is that curve doesn't start off in the correct position for the heart. It's actually an optimization process. It starts off in the position there as a circle, and then iteratively optimizes its position to fit the cavity that the heart is located in. You see, it starts as a circle, the curve, and then as we run the optimization, it fits into that cavity. Okay? So that curve is what we call an active contour or a snake. You can think of it as a little bit like an elastic band that stretches and optimizes its position within the image to snap to the object of interest. The particular type of contour that we're going to use for this snake is a Catmull-Rom spline. If you recall from the mathematics we did last time, the Catmull-Rom spline is a piecewise cubic curve that interpolates through all of its control points. So these control points are the vectors that go into that G matrix, and they're indicated here as little blue circles on this image. So we're going to learn today how to define a snake, an active contour, stretchy curve if you like, on the image, and then optimize its position to snap to strong edges in the image, which in this case was the heart. Everyone understand the basic goal there? Switch back to the action capture. Okay, so this is another example on this course of a top-down model fitting process. We discussed these a couple of times before when we looked at things like the Hoff transform. We're defining a mathematical model of a shape, in this case a closed piecewise cubic curve, and then we are optimizing the parameters of that model, which are actually the control points of the curve in this case, in order to fit that model to the position in which it has there's greatest evidence for that shape in the image. Yeah, so it's this kind of top-down model fitting process, and this model fitting process is a process of optimization. And as we discussed previously, we need to know when we optimize a model to fit it to an image, we need to know not only how to parameterize that model, but also how to assess how good a particular positioning of that model is in the image, what we call the fitness function. So, as I say, the parameters of this model, to answer the first question, are going to be dictated by the snake's control points. As we saw, those blue dots on the previous slide, those are the control points that the Catmull-Rom spline passes through. Each of them is a two-dimensional quantity. It's an XY position on the image, and they define the positioning of that red curve that interpolates all of them. So if my snake, my piecewise cubic curve model with a Catmull-Rom spline has n control points, how many parameters are there that dictate the position of that snake in the image? Anyone want to just take a guess? Each control point is two-dimensional. There's n of them. So how many numbers do I have that define the position of my snake in the image? 2n. Yeah, absolutely, yeah. We've basically got a set of XY coordinates for every control point that determines the position of that snake. Okay, so when we figure out what the best set of control point locations are, we'll come back to this that point in a moment. We need to figure out, given a particular set of control point locations, how good a control point that snake is. And in order to do that, we evaluate something called the snake energy function. It looks quite complicated, but actually it's quite easy to understand. It's just a simple summation of three terms. Okay, the first two of these terms are what we call the internal energy terms, and the final one is the external energy. So let's just talk a little bit about what this means. Actually, first of all, I should say, so the way that the summation being performed here is across the entire length of the curve. So what we're doing here is calculating these quantities for every point on the curve, taking infinitesimally small steps, and summing them together. And then this energy term is a score that effectively the larger the energy, the worse the snake is. So what we're looking for is a position for this curve that minimizes this function. Okay. The first two terms reflect the shape of the curve, and the final reflects the position of the curve in the image. So these first two terms are weighted by two user parameters, alpha and beta. It turns out that alpha regularizes the spacing of the control points in our final position of the curve. It encourages even placement of the control points along the length of the curve. And the beta parameter discourages curves from being proposed that have very sharp discontinuities in them, like corners, for example. This final term, and then this external energy term, evaluates how well the curve that's been proposed actually fits to edge information in the image. So the first two terms are determined entirely by the first and second derivatives of the proposed curve. There's no image information considered in there, yeah? But then the final term is evaluating the image information given a curve. Does that make sense? So maybe I should just give you another repetition of the high-level vision here. What we have is an optimization process. We want to fit a curve to edges in an image, to a shape in an image, okay? We have a process, an optimization process we're going to be talking about in a moment, that repeatedly proposes solutions, positions for that curve in the form of sets of control points. Given a particular solution being proposed, we evaluate this function to score it. The higher the score, the worse the curve is, yeah? How do we score it? We score it based on how evenly the control points are placed around the curve, which is evaluated by this first term, how much curvature there is in the curve, basically how jagged the curve is, that's the second term, and then also how well the curve actually fits onto edge information, evidence in the image, which is this third term. And these weights on those three terms, alpha, beta, and gamma, are set by us as the designer. We basically tweak them to get the best performance of the system. We'll come back to that later. Okay, so let's look at this in a little bit more detail. As I said before, if I have a contour here on an image, then it's a curve in 2 dimensions, and the position of that curve, here in green, is defined entirely by these control points that the Kaplan-Rom equation forces the path of the curve to interpolate with C1 continuity. So as we said, if we've got n control points, then because each control point has an xy coordinate, we've got 2n numbers that represent uniquely the position of that curve on the image. So we can consider a curve to be represented by a single point in a 2n dimensional space. Yeah. If I think about serializing all of these control point locations into a big long vector x1, y1, x2, y2, all the way up to xn, yn, that big long vector is a point, has 2n numbers, so it's a point in a 2n dimensional space. So this curve, for example, might be at this point here in the space, but some other curve might be at this point here in the space. Another curve that looks like this might be at a completely different point in the space. And one of the things that we can note about this space is that it is smooth, okay, which means that similar looking curves map to similar points in this space. This makes sense if you just think about, if I took this curve here and I adjusted the position of this control point just a little bit, okay, that's going to map to a very similar location in this 2n dimensional space. It's going to give me a very similar contour on the page. But a contour that gives me a completely different shape will map to some totally different location in that 2n dimensional space. So, in summary, our process then of fitting a snake to an image is to search this 2n dimensional space to find the point in it that minimizes that equation on the previous page. It gives me the minimum E, snake energy function. Does that make sense? Okay, so let's talk about how we do that. Oh, and this is my point, sorry, here, just saying that the space is smooth, there's similar curves up to similar points. Okay, so in order to fit the curve, the snake, to the best possible position in the image, we're going to employ an optimization technique called gradient descent. Okay, now the gradient descent is going to search this 2n dimensional space for the point that gives us the lowest E And we're going to start off the search at a particular point in the space. Now, normally with the snake, what we'll do is initialize the position of the snake to be basically a circular shape that is larger and centered upon the likely location of the object in the image. So in that heart example, we had a circular snake that was centered pretty much in the middle of the image, and we made it sufficiently large that it would shrink and snap to the object. So let's discuss this gradient descent process, but let's pretend for the moment that our 2n-dimensional space, we're going to simplify our problem. So let's pretend that we've just got one control point in our snake. Okay, that's, obviously pointless snake, because it's just a point, there's no curve there at all. But let's just pretend that we can represent the curve in a two-dimensional space. Then this x1 and y1 here are the space we need to search, and this axis here is a function of that x1 and y1. Specifically, it's this equation E that we just saw, which tells us how good that snake proposal is. Okay? Now, there's going to be some bad solutions in that space and some good solutions. The bad solutions, the bad snakes, are going to give us a high E. So they're the points that are positioned highly on this axis, the red points. But down here in this example, there are some good solutions as well that give us a low E. And because this space is smooth, because similar points in this space will give us similar contours on the image, it's reasonable to, similar points will give us similar values of E. Yeah? So if that wasn't the case, this space would be highly turbulent, and we wouldn't be able to do what we're about to do, this gradient descent operation. Okay, so what is this gradient descent operation then? Well, what we're doing is we start at a particular point, which might be the point corresponding to a large circle in the image. Okay, and what we're going to do is look around that point to find better points. Specifically, what we're going to do is we're going to take this point here, which has some location x1, y1, and we're going to just add a very small amount to x1 to evaluate what our snake would score, what we get for our E, if we were actually not at x1, y1, but x1 plus delta y1. Yeah? That's going to tell us, so we've already computed what our energy, our score for our snake is at this point. What we're going to do is compute what it would be were we to move our point slightly in this direction. We're then going to do the same thing, but we're going to move slightly in the y direction. Okay, so we're going to evaluate our E at position x1, y1 plus delta. Yeah? And that's going to allow us to calculate the gradient in that space. In other words, the first derivative of E, our energy function, with respect to x and y. So each one of those calculations there, the two calculations I just talked about, where we shift a little bit in the x direction, a little bit in the y direction, we're actually calculating the partial derivatives of E with respect to x1 and with respect to y1. Does that make sense? Yeah? Okay. And then we're going to move in the most promising direction. So let's just, again, simplify the problem even further. Let's imagine that our snake is now defined, this is just impossible now, let's imagine our snake is just defined by a single number, x. Okay? So our search space is one-dimensional, and our evaluation, our energy function, is conditioned just purely on this one variable here, x. Okay, then what we're looking for in this space is the point that gives us the lowest E of x. Yeah. So if we start off at a particular position here, this might correspond to our circle, for example, and we evaluate delta E, delta x, then what we want to do is move in the direction, basically negative delta E, delta x. It takes us in a direction that will minimize our E. Does that make sense? Yeah? And if we keep doing that, what we should do is end up each time in a position that gives us a lower, an x that gives us a lower E score. Right? So what problems do you foresee with this approach? Local minima, yeah, absolutely. So we're looking for a minima in this function. This is what we call the global minima, because it's the lowest point, were we able to inspect all solutions, it's the lowest point. But there are clearly going to be other points here, well, potentially going to be other points here, that will attract our x, but may not lead to a local minima. So we call those local minima and global minima respectively. So what this means is we need to be a little bit careful about where and how we initialize our snake, and we'll come back to that point later on. But just going back to our two-dimensional example now, so this is our fictitious example where we think that a snake can be defined entirely by one control point, which is complete nonsense, but it simplifies the presentation for this lecture. We're going to have this space x1, y1. We've got a point here in red, which is our point of our current configuration of our snake. And as I say, we're going to add a little bit to our x1 down here to compute E at x1 plus delta y1. That basically is differentiating our E, taking finite differences to approximate the differentiation of our E with respect to x1. And we're also going to calculate this E x1 y1 plus delta, which is going to be, again, it's like a finite difference approximation to the first derivative of E with respect to y1. Those two numbers then we've got are basically a two-dimensional vector that tell us which direction we need to move in our parameter space, in our two-dimensional space x1, y1. And we're going to jump in that direction. So let's suppose that the first number is 0.9, that's the result of our delta E, delta x1, and our second calculation gave us 0.1, which is our delta E, delta y1. Then our vector would be what we call a gradient in our space, would be the vector 0.9, 0.1. So we would move negative 0.9, 0.1 to move to a value in a position in that x1, y1 space that has a lower E score. Does that make sense? Anyone got any questions on that before I go further? Does everyone see what's going on here? So this red point is a particular curve. We've modeled it in a high-dimensional space, and we're moving around that high-dimensional space to find better curves that give us lower E's by moving it in the direction of, descending in the direction negative the gradient. So it's gradient descent. So this is an optimization process. And we'll just keep doing this until we jump to better and better solutions. We'll stop after a finite number of iterations. Okay, but back to reality. Of course, our snake is not modeled by a single point, control point. It's modeled by n control points, as we discussed at the beginning of the lecture. So in fact, when I calculate this gradient, I'm not calculating it as a two-dimensional vector. It is a vector in 2n-dimensional space. So we need to not only think about delta E, delta x1, and delta E, delta y1, but also delta E, delta x2, delta E, delta y2, all the way up to n control points. So this vector then that we calculate by computing all of those finite differences, by approximating all of those partial derivatives of E, that is our gradient vector. And that is the direction we jump in the opposite direction, in fact, to that gradient in order to perform gradient descent. Does that make sense? So we might start off here. We might then measure that our gradient is in this direction. So then we'll jump to a new point in that space that gives us a lower E, and so on until we optimize the position in 2n-dimensional space, which gives us a curve that fits better and better onto our object on our image, as defined by this function E. Yeah? Any questions on that? Okay. So so I kind of already covered this. So yeah, how do we compute the gradient? Well, we just make these small movements on x1, y1, x2, y2, all the way through to xn, yn, to approximate those partial derivatives in each case by a finite difference. Because we can't differentiate that function fully, right? We could differentiate the first two terms of E, but we can't differentiate that function that the gamma was weighting because it's somehow like looking at the content of an image. We can't really write an equation for that. So we use finite differences for that. So here's that snake energy function again. Let's remind ourselves what this E is that we're minimizing. We're saying given a curve, given a point in a high-dimensional space, we're going to iterate along the path of that curve, summing up these three quantities. The magnitude of the first derivative, the magnitude of the second derivative, which remember is the curvature of the curve from the Frenet frame. And then this final quantity here. And what I've done here is I've just written this function I around the curve, where I is some function that returns a low score if the curve is well positioned. It covers a lot of edge information in the image. So let's not worry about how we go about actually computing that I. What we might do is we might render the curve and look and see which pixels it passes through. We might add up all the edge information, the edge magnitude information under that curve, and then make this function return something that's like 1 over that. So that the more edge information, the lower the score, for example. But there are many possible solutions to that external energy term. Yeah. Well, the alpha, the beta, and the gamma are just numbers. They're just scalars that the user or us as the designer set in order to govern the relative importance of each of those terms. It's just the weighting, that's right, on each of those alpha, beta, and gamma are just weights. Yeah, they're just scale factors. In a moment, we'll see the effect of changing those weights on the snake's behavior. In fact, right now, we'll see it. In fact, this slide. So, if we have a low weight on alpha, then what that means is we don't care so much about penalizing that first derivative term. And what that will lead to, as we'll see, is that the control points on that curve end up being irregularly spaced. That's a problem because if we have a curve and all the control points start bunching up on one side of that closed contour and there are very, very few on the other side, then it's going to be very hard to represent much complexity in the shape in the sparse area of those control points. If we have a low weight on beta, then that means the curvature can be quite high on that curve. Okay, so low weight on beta would mean that the curve, for example, could double back on itself very easily. Instead of having this elastic band, this snake snap onto the structure cleanly, what it could do is snap onto the structure such that it double backs on itself, sort of folds back on itself, which would be an inefficient way of representing that object. And a low weight on gamma, which you really kind of infrequently encounter, means we don't actually care very much about what's in the image, which, we get a nice smooth snake, a nice smooth curve, but actually it may not fit on the object of interest in the image at all. But obviously we do care about what's in the image. That's the point of computer vision. So we would have a relatively high weight on that typically. All right, let me switch to the demo. What's happened here? Top. Okay. Right, let's just figure out which one of these functions to call. I don't know if that's going to work. Checking that's right. So just give me a moment to find this code. Maybe it is happening. Yeah, I'm not super convinced I've got this demo to hand. Actually, I thought I had brought it, but maybe. Okay, what I think we'll do is maybe I'll run that next time. Apologies for that.
Having got a
Well, no. Well, it's 0 to whatever to any value. So they're obviously weighted in relative. They exert a weight that is relative to the other weights. So if I were to have a high value on beta and gamma and a low value on alpha, then I'd end up with an image that looks a little bit like this one here. So we have this red corresponds to the initial position of the snake, and this green corresponds to the position of the snake after 50 iterations of optimization. And what you see is that it's fitted very well to this part of the object. This white here is basically the edge field from an object, so it could be the output of like a sub-edge detector, for example. It's fitted very well on this side, but very poorly on this side, and that's because the control points are all kind of clustered over here, and there's been very few here, so it doesn't have that representative power to snap onto the object. If you look here on this image here on the right hand side, this is a snake that had a high alpha and a high gamma, but a low beta, so that meant that we didn't care as much, we didn't penalise as much high curvature of that curve. What that means is that proposals for curves that do have a high curvature from the optimization will end up scoring okay. And we see here that the curve has basically doubled back on itself several times here on the right-hand side. If we have a low weight on gamma, but a high weight on alpha and beta, we can see that the curve here has got good control point spacing, it's regular, the curvature is controlled, it's not doubling back on itself, but it doesn't fit onto the object at all because we're not taking into account that image information. Yeah. I guess I'll show you that very briefly next time in the demo. I'm not sure where that's got to, so apologies for that. But this is the output of the demo anyway. Yeah.
When we run the gradient algorithm, are we doing that on variations of the alphabet and gamma, or are we doing variations?
Okay, so that's a good question. So just to clarify, we fix alpha, beta, and gamma as design parameters in our system, and then we run the gradient descent optimization to give us proposals for our P of S, our curve. Yeah. Each time we iterate those through that gradient descent algorithm, each time we move our point in that high dimensional space, we're evaluating E. So the space of parameters we're searching in is not alpha, beta, and gamma, they're constant. It's the position in the 2n dimensional space that defines what our P actually is. It's what we're searching. Yeah? Does that make sense? Yeah. Yeah, they're very empirical. Yeah, you end up tweaking those to get the right result. Yeah, yeah. So it varies very much, on the kind of object that you want to detect. If your object had a lot of jagged corners, for example, then you'd want a low beta because you want to encourage it to snap onto them. However, and this brings me to the next point, there is a tweak on this algorithm that makes it a little bit easier to come up with an alpha, beta, and gamma that's just sort of general purpose. And that is this Williams-Shah fitting process. Basically, Williams-Shah algorithm is effectively to perform gradient descent exactly the way that I've outlined it. But during that optimization, which, as I say, may run tens of cycles, each time we run an optimization, we look at these three conditions. And if the following conditions, these three conditions are met, then what we do is we set that beta weight to 0 for the remainder of the iterations. So we come up with an alpha, beta, and gamma. We iterate through our gradient descent to fit the curve. And then if these conditions are met at some iteration, then we just 0 the beta for the subsequent iterations. And what that means is the later iterations will not be penalized at all for having a high curvature. Now, what you see when you run these algorithms typically is that the snake will converge onto the object, and it always gets onto the object approximately well, but then it has trouble snapping to the exact shape of the object, because to snap to the exact shape would require the curve to bend a lot to get to the exact shape, and that increases the curvature of the shape. So this little tweak on the fitting algorithm allows us to basically disable the penalty on curvature later in the iterations, which makes the curve fit better. Yeah. The problem with the gradient descent algorithm, as we pointed out in previous slides, is that it's susceptible to local minima, which means if you don't initialize your snake in a good position, then it's going to snap onto some arbitrary stuff in the image and not onto the object of interest. So typically what we do, and this is a detail that everyone does this, but it's very infrequently mentioned in the papers. So it's one of these things that needs to be known about to reproduce the results. Really, is you have to when you run your edge detection on the image to produce this edge field, you're computing the gamma term over. You blur that edge field very heavily, so that the images, that field kind of radiates out values. You can sort of see it here in these contours here across the entire image. What that means is when I initialize my snake here and I iteratively optimize its position, that gamma term, that external energy term, is going to encourage it to position increasingly bright areas of this image. If this image consisted solely of the edge here and just black everywhere else, there'd be no kind of gradient to converge towards. So this is why it's important to do this pre-process on the edge map prior to fitting the snake. Okay, anyone got any questions on that? Okay. Oh yeah, so I should say, what are those three conditions that allow us to relax the beta? So basically we're looking for situations where if the curvature at a particular control point is larger than both of its neighbours, yeah, then what that means is that curve has already been attracted onto a point of high curvature of the object. So that would indicate it's time to trigger this zeroing of the beta term. Again, if the curvature of any of these control points is not only larger than its neighbours, but also is greater than a certain threshold, we'd also trigger this. And perhaps we'd also put or in fact in the algorithm they also say if a control point is over a really strong edge pixel, then we would zero the beta there as well. Okay, well if there's no questions on snakes, then I want to talk. Yeah, there is a question. Good. Okay. Yeah, all three. Yeah, if it wasn't all three, then as soon as we encountered a little bit of bright speckle noise in the edge field, then we'd immediately be zeroing beta, which would cause a problem. Okay. All right, so let's move on then and talk about the other kind of shape model that's frequently used in computer vision, which is what's called a point distribution model. And you can think of this as a statistical model of shape that can be used in combination with other techniques in computer vision, particularly tracking techniques, in order to make them more robust. In fact, we'll see that they can also be used in combination with snakes to make that fitting more robust as well. But let's not get ahead of ourselves. So what is a point distribution model? It's a statistical model of shapes that's actually built using an eigenmodel. So let's suppose, from a practical perspective, let's suppose that I was tracking my hand moving over a desk, some sort of webcam tracking operation. There'll be certain contours that I can detect in that image that are likely to be hands, and they're going to all look like this. And there's going to be certain other contours that I detect in that image that might be just due to junk that's lying around on my desk due to clutter. And they might look like anything else, like these scribbles, for example. So if I'm tracking or even just trying to detect an object in an image, it would be useful to be able to incorporate some prior information about the likely shape of that object in order to be able to detect it or track it in the image. And that's what this point distribution model, or PDM as it's called, gives us. So the way that we build a point distribution model is, again, to exploit this idea of a 2n dimensional space that models the shape of a contour. So we're going to reuse this idea from snakes, where we have a contour that is a cat-mod-rom spline interpolating an arbitrary number n of control points. Okay, so basically the shape of the contour is, again, uniquely defined by a point in a 2n dimensional space. Okay, and I'm going to train up an eigenmodel to model the distribution of those shapes. So I might take my hand, take lots of images of it, extract the contours, and do all sorts of things with my hand, positions of my hand, and each position of my hand corresponds to a point in this 2n dimensional space. And I'm going to build an eigenmodel up over that point distribution. So that eigenmodel is going to be in 2n dimensional space, and it's going to model that statistical distribution of contours. In other words, it's going to model the shape of the object I'm interested in tracking. We call that model a PDM. Is that clear to everyone? So we're just using, just using eigenmodels, yeah.
Do you think that eigenmodel would be able to detect they don't have that level?
No, so the eigenmodel is not doing any detection per se. What it's doing is modeling the statistical distribution of hand shapes at the moment, yeah? That's all it's doing, yeah? Does that make sense? Okay. So there's a couple of things we could then do with that eigenmodel. One thing is think about the Mahalanobis distance to that model. If I pick a point in this space, in other words, if I have a contour, I can use the Mahalanobis distance, and perhaps this is where your question was going, to measure how likely it is that shape is a hand, based on our training data. But actually, for the purposes of this model fitting of a contour onto an image, we're not really interested in doing classification. What we're interested in doing is somehow constraining the detection or tracking process. And actually, to do that, we need to consider a little bit about what the eigenvectors of this distribution look like. So, what do you think the eigenvectors tell us about this set of contours? What do the eigenvectors of any eigenmodel tell us about the distribution it was trained on? Yeah, the directions in which that distribution varies in the high-dimensional space, yeah? Yeah. And the eigenvalues tell us the variance along each of those eigenvectors. So, if we were to start in the middle of that eigenmodel, at the mean of that eigenmodel, which actually would look like this for a training set of 72 hand contours. If I were to walk along in that two-n-dimensional space, along the principal eigenvector, that would move me through the direction of greatest variation in that space. And as I walk along that eigenvector, I can synthesize, just because I'm moving along in two-dimensional space, I can synthesize a contour from each position in that two-n-dimensional space, because it just gives me a set of control points. I can just draw the spline using Catmull-Bond spline. Yeah. So what I see as I walk along that first eigenvector for this training set is a hand that changes like this. So in that training set, this is the principal mode of variation. If I were to walk along the second eigenvector in that space, which would be orthogonal to the first, and indeed all the other eigenvectors, then what I'd see is the thumb moving in and out. This third one, you've got some sort of Vulcan thing going on, like the middle finger going left and right. Okay, so what we can do then is, in this generative way, model the space of distribution of these hand contours that's being modelled by this eigenmodel. We started off at the mean of the eigenmodel, and then using the matrix U, which you remember the columns in that matrix encode the eigenvectors, we can multiply that U with this W here, which corresponds to a vector of weights, each one of which multiplies against an eigenvector in order to move us. So for this example, the first mode of variation here, I had a vector W that was 1 hot for the first eigenvector. So it was like 1, 0, 0, 0, 1.1, 0, 0, 1.2, and so on. As it would scale me along that first eigenvector as I move through the space. To get the second mode, it would be 0, some number, 0, 0, 0, all the way to the end, okay, and so on. Yeah? Does that make sense? All right, so you know what? I'm tempted to stop there given the time. How much time have we got? Yeah, no time. So let's not rush it. Let's just summarise what we've seen today. We've seen that it is a useful technique to be able to model the shape of a contour using a 2 n-dimensional space for an n control point contour. We've exploited that model of a contour in 2 ways today. The first was for snakes, sometimes called active contours, which allow, basically we perform gradient descent within that 2 n-dimensional space to fit the curve to a contour, to edge information in the image. The way we do that is using the snake energy function, which is a way of calculating how bad a snake is, okay? And it's a combination of the derivative properties of that snake, things like its curvature, and how well the curve fits to edge information in the image. The other application of this 2n dimensional space modeling idea for contours is these point distribution models, PDMs, that allow us to model the statistical distribution of a set of shapes, like these hand shapes here. I've told you that we can exploit that statistical model of shapes to make trackers and detectors more robust, but we haven't yet seen how to do that. We'll talk about that next time. Okay, let's leave it there. Thank you very much.